Okay, so we've got a few little lessons here on the birthday problem, which is another one of these famous problems in probability. So you should know about it as part of your general mathematical literacy. But it's also a problem that has some interesting implications that we'll talk about in the videos that follow this one. But first, let's just say what the problem is. So the question has to do with how likely it is for people to have the same birthday. You meet somebody and they have the same birthday as you, and it makes you feel like there's a bond. Oh, it's so exciting. Um, and the question is, well, how unusual is it for people in a group of a certain size for there to be some people that have the same birthday? Okay. So let me restate that same question in a slightly more precise way that's going to allow us to actually calculate the probability. Okay, so the question is, how many people do we, spell we right? These two-letter words are really tough. Do we need for the probability that at least two have the same birthday to be at least 50%? Okay, so it's kind of a complicated question. Okay, we want to know how large the group has to be for this probability of some shared birthday to be at least 50%. And the way the question is set up makes you think that as the group gets bigger, that probability is getting bigger, and that makes sense, and it is in fact true. What is maybe more surprising to most people is that the answer is 23. The answer is not a big number. People often guess that it has to be 365 or 365 squared or some really big number because it just seems like it's a pretty rare event. Okay, so let's set up the model that convinces us otherwise. So for the model, what I want to assume is, for think uncontroversial things, although the first one isn't quite true. We're going to say that there's 365 possible birthdays. So sorry to any of you leap day babies out there. You're not counting. We're counting you as March 1st. We're counting people who are born on February 29th of a leap year as having the birthday that I guess they would celebrate in other years. We're also going to assume that the birthdays are all independent. Okay. So each person's birthday is independent of all the others in the group, and that each day is equally likely. That may or may not be true. I don't know if there's sometimes a year where more babies are born than others, but we're not paying attention to that now. We're just looking at the simple model. Okay, and so let's think about first two people. Two people is pretty easy. You can think about it two different ways. One is you can just think about what's the probability that the second person's birthday is the same as the first. So the first person's birthday is what it is, and the second person has a 1 in 365 chance of having the same birthday. That is 0.274. It's pretty low probability. Okay. The other way you could think of it is that there are 365 pairs of possible birthdays for the two people. So we might call that a birthday profile. Okay, so a birthday profile, if it's two people, it consists of my birthday and your birthday. So there's 365 possibilities for me and 365 for the other. person. And in how many of those profiles are they're the same? Well, there's 365 of them. Okay. There's the possibility that we both have the same birthday and it's January 1st. We both have the same birthday as January 2nd, January 3rd. I don't have to go through all of this. What's in the numerator here is the, so if this is the total number of birthday profiles possible, this is the number of profiles with both the same. Okay. And that, of course, reduces to the same. Okay, so with two people, no big deal. It's easy to calculate, but that's not very interesting. It gets a little more complicated as the number of people increases. So there's three people, you have to think about the probability that all three have the same, that the first two have the same and the second is different, the second two have the same and the first is different, the first and third have the same and the second is different. Okay, that's, I can imagine writing that out. It'd be kind of a hassle, but it would be doable. But then it gets worse. If you think about four people, there's the probability all four are the same. There's then the probability that the first three have the same and the second one is different, and other three. It gets extremely messy. So let's go to a new screen here. There's an easier way to think about that whole problem. What we're going to do is calculate the probability that all the birthdays are different, that no two people in the group have the same birthday, that each, and however many people we have in the group, each one has a unique birthday, and we're going to subtract that from one. Okay, so that's one of our favorite tricks. We love it. We can do this, and it really does help with the birthday problem. So doing it that way, let's start kind of just thinking about this again, sort of starting with three people, building up and seeing what the pattern looks like. So for three people, again, we'll sort of think about the number of possible birthday profiles. So person one has 365 possible birthdays, person two has 365 possible, person three has 365 possible. So we've got 365 to the third power here. So again, it's the number of possible profiles. And just as I did before, when I say profile, I mean a value like for each person. And then what we want in the numerator now is the number of profiles with no two the same. Okay, so with three people, let's think about this. So there's 365 possibilities for the first person. Once that person's birthday is taken, since we're looking for the ones where there's no two the same, now there's 364 possibilities for the second person and 363 for the third person. Okay, and that's right. That is what the probability is for four people. Okay, so now the number of possible profiles for four people is 365 times 365 times 365 times 365. Fourth power there. There's 365 possibilities for the first times 364 times 363 times 362. Okay, so what's going on in the numerator here is we have 4 factors. We have as many factors in the numerator as people. Okay. I think I'm already seeing the pattern here. I think I'm already pretty comfortable saying that when we have X people, the denominator is 365 to the X power, and the numerator starts with 365 multiplied by 364 times 363, and it has X terms in it. Okay. So it's kind of the same, we're gonna do the same neatening it up trick that we did in writing the combinatoric formula here. We're gonna notice that this is 365 factorial with 365 minus x with all those lower terms removed. Divided out. So we can write that very nicely as 365 times 364. 364. Boy, hard thing to write, it turns out. 365 times 364. I said I was going to write it out nicely. Let's just write it out nicely. Going back to my thread, we know that the number of profiles with all the birthdays different is 365 factorial, missing the last 365 minus x terms. So this is what I was trying to do in the first place. It's 365 factorial divided by 365 minus x factorial. And then I've got the same 365 minus x here. Okay, so this part is my numerator, and this part is the denominator from the original fraction. Okay. So that's the number, that's the probability for birthdays. If we want to be even more general, let's just think about the general version of the problem we're talking about here. Is this, given an attribute that takes n possible values, each with equal probability, the likelihood that all are different in a group of X, I need to emphasize, group of size X is n factorial divided by n minus x factorial n to the x power. Okay, so the birthday problem is just a special case of this where n equals 365. But we could think about other things that people could have with equally likely probability, and this would be the probability that probability that no two are the same. So if we want the probability that at least two have the same birthday, ballot, whatever it is, it's 1 minus n factorial over n minus x factorial times n to the x power. Okay. That's the basic birthday problem. I'm going to pause here. There's two other kind of separate marks that I want to make that'll separate into their own videos. So I'll see you in those.